Right, so today I am going to discuss the question number 2 of mechanical vibration paper, right? The year is 2013, right? So the problem that I have already sketched, right? So now this is the problem, right? Here we have a mass m, and in the other side also we have the same mass, right? So now here you can see these roller paths, right? So let's call it roller path or whatever, right? So along this path, right, this mass can move, right? Here also, right, along this path this mass can move, right? But that doesn't mean it can move whatever the amount or whatever the distance, right? So anyhow the motion is limited, right? So when it is like that, so don't think that it can go along whatever the distance, right? Anyhow it can move, but the motion is limited, right? Okay. And now this is the pivot point, right? That means here you can observe this let's say this bar or beam or whatever. Now this is a beam, right? Okay, but beam and bar are two different things, right? Okay, so in a future video I will explain that. Just for now, just take this as a bar, right? Okay, right. So now you can see each of these masses, right? So let's consider this one, right? Because first of all you have to identify this mechanical system, right? So here we have the mass and we have a roller path. This mass can move along this roller path, and this is connected to this bar. So this is the bar, right, through this spring, right? Okay, so here also here we have the mass and it is connected to this bar through a spring, right? So what is this? This is a spring, right? Spring, right? Okay. And what is this one? What is this plate, right? What is this plate? Plate, or let's say some how to say that, that is something like, okay, it's better we will consider this as a, let's say something like a roof, right? So let's call this part as a roof, right? So something like the roof. Okay, so that's it, right? And also carefully focus the length, right? So this line that you can see from there, right, this represents the center line. So let's say like that, right? The distances you know, right? I think that's it, right? I hope all the other remaining information and other facts are clear to you, right? So before solving this type of problem, right, the most important thing is that first of all you should identify the mechanical system in machine vibrations. This is very much important, right? First of all understand the system. Don't memorize. Like based upon my experience, this is what I have really seen, that don't memorize the equations or the steps, right? Because you cannot do like that. Okay, identify the system and then we will see how to apply the equations of motions, right? I will teach you everything, right? So no problem, right? Done.
Okay, so we know that this is the original position of the mechanical system, right? So now we will think that, or we will just say as the starting point that this bar is turned or is pulled toward the upward direction by an angle theta, right? So now this is that angle theta, right? So as you can very clearly see, now you can see that the bar that was originally like that is now turned by an angle theta towards the upward direction, right? Okay, so that is the first thing that you have to understand. Okay, right? So now when this bar is turned upwards, then you can see here we have a spring, right? So now this spring will get extended. Is that clear? Right? And the spring that we have at this position is getting compressed, right? I hope it is clear. This spring will get extended, right? And this spring will get compressed, right? And on the other hand, if you're going to consider the same scenario to the other side, right? Because at the other side also we know that we have two springs, right? one is below the bar and one is above the bar, right? So then what will happen when it is turned by an angle theta like this? This spring, right, will get extended while the spring over there will get compressed. So like that is how you must analyze the system, right? So do not try to memorize the equations, just analyze the equation like that. Okay, so now let's apply the equations of motion, right, for the motion of this bar, right? Okay, so now just focus this bar, right? So now it can be very clearly seen that this bar is rotating along the anti-clockwise direction, right? Okay, so that is clear, anti-clockwise direction, right? So now let's apply I theta double dot towards the anti-clockwise direction, right? So now what is I there, right? This is not second moment of area, actually this is the moment of inertia of the bar. So what are the units? kgm squared. Then what is this theta double dot? This is the angular acceleration. What are the units? Radians per second squared, right? Okay, so that means definitely here you are getting the dimensions of torque, right? Okay, because this is kind of a rotational motion, so this rotation is caused by the torque that is generated, right? Okay, so actually this represents the resultant torque, right? I theta double dot towards the anti-clockwise direction, right? So now let's apply the other forces that are generated such that the resultant is I theta double dot. So this is how we should explain that, right? So now just think that here you can see this spring, right? Okay, so now there is something that you have to understand very clearly, logically, right? So now when this bar rotates in the anti-clockwise direction, you can very clearly see, as because this bar is attached to the spring, right? When this bar is rotating, like it is something like this bar pulls the spring towards the upper direction, right? Is that clear? This bar actually pulls this spring toward the upward direction, right? So that means this bar is actually exerting a force. That means this bar is actually putting a force like on the spring towards the upward direction, right? So because of that, the reaction force that is given onto this bar by the spring is towards the downward direction, right? So I hope you got it. So in case if it is not clear, you can again rewind and see, right? So this is the same logic that is applied there. Okay, so let's consider for this spring, right? So here also you focus, right? It is that is also very clear. Now due to the rotation of this bar towards the upward direction or towards the anti-clockwise direction, you can very clearly see that this bar is actually attached. This bar over there is attached to the one end of this spring. So due to this rotation, right, this bar actually compresses this spring, right? So because of that compressive force, right, this bar is exerting a force on the spring towards the upward direction, right? Let me lock the screen. This bar is exerting a force on the spring towards the upward direction, up, right? So then the reaction force that is exerted by the spring on this rod or bar is towards the downward direction. So that is how you explain the generation of forces, right? So I hope that is clear. So that is why in every time, like when you're going to equate the resultant torque scenario, right? So that means like all like this resultant torque is generated by all the torques that are generated within the system, right? So that is why in front of all these forces, because now here you can see that one force is generated because of the reaction given by this spring, then another force is generated on the bar
because of the reaction given by this spring, right? And again by this one and this one, right? So that is how the force equation, because now there's a special case that we have to consider. Here you can see, here we have the mass, so we have to consider the linear motion of the mass also, right? So then it is little bit complicated how to consider the distance. I will teach you that later. So first focus how the forces within the bar are generated, right? So that is the part that I want to teach you, right? Okay, right. So now we will see how to apply the equations of motion, right? Okay. So now what is our first formula? The very first formula is that we are going to apply this I theta double dot, right? What is the direction? Towards the anti-clockwise direction, right? So this formula we are going to apply to this bar, right? Because when you are going to consider this problem, right, basically there are three parties in this problem, right? The first party is the bar, the second party is the mass that is over here, then the other mass is the mass that is over here, right? First we will consider this bar, right? So now if you are going to consider the rotation of this bar, right, because you know that initially the bar was in this position, right? So now this bar is turned by an angle theta, right? Now see, that is that angle theta. Initially it was here, now it is turned by an angle theta, right? So actually this rotation is caused by there are certain forces, right, that are actually responsible for this rotation. So actually those forces are caused by these springs, right? So what are those springs? See, one spring is here, another spring is here, another spring is here, and the last one is here, right? Right, okay. So now I will teach you a special concept called relative end attachment theory, right? So let's see what is this, right? So now you consider this spring, right? So the force that is generated by the spring is actually caused by the spring constant, right? That is K, and the extension of this spring, right? Okay. So now just consider this one spring, right? So let's consider this one. So now here you can see that there are two ends of this spring, right? That means this is one end and this is the other end, right? Okay. So now you have to consider, or you have to give some consideration, right? What are the types of extensions, right, that are undergone by the spring? Considering the extension that is undergone by the end over here, that means this end, and the extension that is undergone by the other end, which is this one, right? If the right side has moved upwards, that means definitely this left side must move downwards, right? This side upwards, okay, and this side downwards, okay, right? And I hope you got it, right? Okay, so now let's see how to apply this what is this I theta double dot formula about the pivot point, right? Okay, so actually what you're going to apply there, this is all about moments, right? Okay, now let's see how to apply, right? So what is moment? Force into perpendicular distance, or in other words you can say distance into perpendicular force, right? Whatever, right? No problem. So we are going to apply this to this this bar, right? We are going to apply I theta double dot formula to this bar, okay? That's what you can see from here, right? So total how many forces are there? 1, 2, 3, 4. 4 forces are there that are generated, that are actually caused because of the 4 springs, right? 1, 2, 3, 4, right? Okay. So now application is not that it's not hard, but you have to know how, you must know how to apply, because you know you have to consider that relative displacement scenario, right? That is the problem. Okay, doesn't matter, let's see.
Okay, so let's focus what is the first force that I have applied there, right? Okay, so now fine. Okay, so now I will first consider this spring, right? Can you see this spring? Right. Okay, so now as according to the present structure, you can see that this bar, which was originally like this, has now turned like this, right? Now turn like this. Okay, so now when it is turned like that, now you can very clearly see that this bar actually presses this spring over there, right? Okay, this bar presses the spring, right? So the reaction force exerted on the bar by the spring is along the downward direction, right? Reaction force that is exerted on the bar by the spring is along down direction, down, right? So but now carefully see this I theta double dot you are going to apply along the anti-clockwise direction, right? This is the pivot point, right? But you are going to apply this along anti-clockwise direction, so the force will be negative, right? Is that clear? Right, so how to find the force? So how to find the force means, like, you know the spin, like stiffness, you know, oh, let's say spin constant, right? So that K constant, you know, right? So what is the force? The force is that spin constant multiplied by the particular extension, right? So now you know the force. So now you know the force, right? So then that force into the perpendicular distance, right? So as here in this problem, what we are going to consider is the force and distance we will take perpendicularly, right? I think then that is easy, right? Okay, so now first consider this spin, right? Okay, now here when considering this spin, okay, see in this spin, like one end is here, other end is here, right? So because of this end over here, as you can see, there is no any displacement caused because of this end, right? So the displacement is only caused because of this end, right? Okay, so what is actually that distance? What is actually the displacement? So for that we are going to use S equals R theta formula, right? You know that, okay? Or in other words, now see, now if this is the originally the bar is at here, this L from this center to here, that is the L, right? So this L can be considered as the radius, right? So what is this length? S equals R theta, that means L theta, right? Right, so now what is the extension? L theta, right? Something like similar to the arc length, right? So minus, why minus? Because the direction is negative, right? Minus K times L theta, so that is the force, right? So minus K times L theta is the force, and what is the distance? So distance, you have to consider the perpendicular distance. So this is L, what is the perpendicular distance? So that is L cos theta. L cos theta is the perpendicular distance. So minus, carefully see, minus K times L theta, this part stands for the force, then L cos theta. Now here I have put cos theta to the beginning, it doesn't matter. So L cos theta, that stands for the perpendicular distance. Is that clear? Right, I hope it is clear, right? Okay, so now let's focus the second part, right? Okay, now here, now see, there's a problem here. Now consider this spring, right? In this spring there's a serious problem, because now if you're going to consider this spring, okay, see, when considering this spring, there are two ends, one end here, other end here, right? So there is a displacement caused by this end also, there's a displacement caused by this end also. So but when applying it as a force, you have to consider the relative displacement, right? Actually that is the point where most of the students will find like difficulties. Okay, doesn't matter, it's not a serious problem, right? Here also the direction will be negative, right? Because the force exerted on the bar is always along the opposite direction because of the reaction, right? Because, like, shall I teach you that again? Now see, the bar is originally here, right? Now when it is turned like that, right, actually the spring is pulled by the bar along the upward direction, right? So the reaction exerted by the spring on the bar is along the downward direction, so that is why it is negative, right? So now here the problem, right? Now see, in this case, right, there is an extension of L theta from this corner. What corner? This corner, right? How did you know that? Because you know this is the angle, right? We are going to use that that formula. See, if you are going to consider this circle, this is radius, this is theta. So what is this arc length? This one. What is this arc length? S equals r theta. So that is the concept we are going to use, right? So we know that here the distance is L theta, but now the problem is, in addition to this L theta, there is another displacement cos because of this mass, that is also along the upward direction. What is that value? x1, right? Because the displacement caused by this mass is x1 along what direction? Along upward direction. So you cannot consider two displacements at once, so you have to cancel one, right? Okay, so that is the technique, right? Because like at this time, this end, now if we're going to consider this spring, at the same time this end is extended by L theta distance, and in addition to that this end is also like extended by x1, so you cannot consider two scenarios, so you have to cancel one side. So better cancel that x1, right? Because what is the reason? The reason is now you are going to apply this formula to the bar, not to this mass, right? So you have to give priority to the bar, so you have to cancel this now. L theta is from this end, x1 is from this end, so put x1, just how to say that, just add a distance x1 along the downward direction to both here and there, so then you can have the relative value. I hope you didn't get that. Wait, now you will get it. Now if we're going to consider this end, right, so this is the center, let me sketch that nicely. So now this is the bar, this is the center, right? So this is the spring, right? So this end causes a displacement x1 upwards, right? And this end also causes displacement L theta upwards. So you cannot consider two at once. So in order to cancel that, add x1 downward to both the sides, x1 downward to both the sides. So what is the resultant on this side? So resultant on this side will be L theta minus x1 along the upward direction. I hope you got it now, right? So that is the technique that is used there. See, minus L theta minus x1 times k. What is k? The spring constant, okay. What is L cos theta? The perpendicular distance, right? So that is the same scenario that is used. See, right? That's the same scenario that is used, okay. So then you have to apply the same equation to this spring and as well as to this spring, right? So in this spring also that scenario is there, because there is another displacement x2 because of this mass, right? Okay, so let's analyze that also. Okay, what about this spring? Oh, this spring, it is easy, right? Because like this end is attached to this roof, this end is attached to there, right? So now again I will explain that part also, because if you are going to consider the bar, originally it was here, now when it is turned like that, right, originally the bar is in this position, now when it is turned like that, now you can very clearly see that this spring is extended down in the downward direction, right? It's like that, this spring is extended in the downward direction by the bar. That means this bar is pulling this spring down, so the reaction on the bar is on the upward direction, so force is negative, minus k times L theta. So what is this arc length? Arc length means what is that displacement? Here the angle is theta, radius is L, radius means the length from here, this center to this end, so the displacement is L theta minus k times L theta times L cos theta, but I have written cos theta to the beginning, right? Actually it should be L cos theta, because you have to consider perpendicular distance, right? Got it? And the same scenario is to here also, right? Because here what we have, I hope now this is clear, right? So please look at here again, right? So if you can understand this concept, then the situation is done, right? Okay. And then let's consider the last part, right? So here also you can see the bar is originally in this position, right? And it is pulled down. Oh, this bar actually pulls the spring down, right? Okay. But when you're going to consider for this spring, right? Now see, just focus this spring. Now when the bar is turned like that, this bar presses this spring, right? This bar presses this one. Okay. So the reaction on the bar is along the upward direction done. And in addition to that, now carefully focus. Now when considering the motion of this bar, right, which was originally here, okay, when it is turning like that, now these are the logical points that you have to consider, right? So that is why most of the time they make failures in attempting this type of questions, right? So the bar is originally here, right? When it is rotating like that, then it is something like, common sense. You have to think that in order for that motion to happen, this mass should go up and this mass should go down, right? Now you got the point. This mass should go down. So to that we have to give a different identification, right? Some students are putting same value, those are the common mistakes, right? Some students are putting, same value here also x and here also y. That is wrong. Here you have to put a different value, right? Because that is, common sense, right? So this is x2, right? So now if you are going to consider this spring, right? This spring is actually pressed by this bar by a distance of L theta from this end, right? Can I get a paper? And I will teach you that also, right? So now I'm talking about this spring, okay? This one. So now this spring is there, right? So now this spring from this end, the spring is pressed down by L theta, and this end is also extended by a distance x2. So what you have to do, just cancel one. So how to do that? We know originally L theta going downwards, right? Is it downwards? Yeah. And originally x2 also going downwards. Okay. So what you have to do? Add x2 along the upward direction. Add x2 along the upward direction. So this side will cancel. So the remaining will be the resultant of this situation. The resultant of the situation over there will be L theta minus x2 along the downward direction, right? I hope you got it right. So that is how minus k times L theta minus x2 times L cos theta. So what is L cos theta? Because this is the length L cos theta. L times cos theta, L times cos theta will give the perpendicular distance, right? Because we are going to take the moment about the center. I hope that part is clear, but make sure this cos theta does not equal to 0, right? That is why it took this much of time for you to explain, right? Because I know students will never understand this. That's the problem. Okay, student, now the part is the simplification. If you simplify carefully, right? See people, now carefully simplify, okay? If you simplify carefully, now that is the problem. If you could not simplify, definitely you will not be able to reach to the answer, right? Okay, so now if you simplify this statement, you are getting something like this, right? Just do the simplifications, right? So then shall you see how it comes? It's easy, right? It's not hard. Just carefully follow the steps. Focus this step, focus this step, and now the funny thing after that. So now this is about the concept called degree of freedom, right? That is like different ways how you can define the motion. So now here, now at the last step, nicely separate the directions, like theta times what, x1 times what, x2 times what, because that information we need in order to obtain the matrix, right? Okay, so what must be the final answer? I'm going to stop the video from here, right? So the final answer for the moment equation is I theta double dot, because like this equation must be right? You have to equal this side to 0, right, in order to form the matrix, right? So what must be the final equation? I theta double dot plus theta times 4kl squared plus x1 times minus kl plus x2 times minus kl equals 0, right? Now try to obtain up to this level, right? Okay, then after that I will discuss this one and this one later. Okay, right, so let's continue from here. I think I have obtained the equation up to this I theta double dot along the anti-clockwise direction, right? That means I have applied the equation to this bar, right? So now we have to apply the equation to this mass that you can see there and to this mass, right? Okay, so first let's consider for this mass, right, mx1 double dot. Now okay, that means I have to consider this one, right? So now just consider this one. Now based upon the present direction that you can see from here, right? So now we know that this beam, right, rotates like that, right? Now you know that this beam rotates like that. Okay, so now if it rotates like that, then what you can see is this mass m moves along the upward direction, right? Okay, but I told you that according to the relative end attachment theory, now if you're going to consider this spring, right, if this spring is subjected to two different pullings or pressings, right? So now in that case, what you can see, if you're going to consider this spring, right, you can very clearly see that this mass m also presses the spring, and in addition to that, the spring is pulled by this rod also, or this beam, right? Okay, bar, whatever, right? So now, but when you're going to apply, now here what is the subject here, right? Now there is something called subject, right? So now our subject, that means now we are going to give priority to this m, right? So now focus here. So now we are going to give priority to m x1 double dot, because now x1 is the direction or x1 is the displacement, right, that we where we give priority when considering the direction or when considering the direction of motion of this m, right? So we write the equation like by saying, now carefully see, now we write the equation by saying m x1 double dot, and what is the direction? Along the upward direction. What is the direction? Along the upward direction, right? So that is why I have written m x1 double dot, and then you have to specify the direction, upward direction, right? So now this mass is attached to I would say that this mass is attached through this spring, right? And now you know this spring is actually subjected to two different displacements, right? One is because of the pressing, one is because this spring is pressed by a distance x1 from this due to the motion of this mass, and other one is because of the because of this pulling displacement by this bar. And we know that displacement by using the equation s equals r theta. So what is that? What is that value? S equals r theta means L theta, because we know that this is L, this is the angle. So what is this arc length? So that is L theta, right? S equals r theta means L theta. So now I told you at one particular time you are going to consider only like one displacement. That means you have to stop one guy with respect to other. Now you understand? Now if you are going to consider this end, right, so this end is pulled by this bar by a displacement of L theta, and on the other hand this end is also pressed by this mass by a distance of x1. Agree? So but you cannot consider two displacements at once, so you have to cancel one, right? So this end is moving along upward and this end is also moving along upward direction, so you have to cancel one, mean just put a negative direction. How to say that? Okay, so I will write it here, right? So just hold on, I will just write it, right? Just focus here. Now if you are going to consider this spring, right, so now this end along this direction having a displacement of, what is that? That is x1, right? Right, and this end is having a displacement along this direction by a displacement of L theta. So just you have to cancel one. That means put a negative one to this end. Is it clear? Put a negative one to this side, and like give, this is the way, right? Give a displacement L theta along the negative side to both these ends, right? Put L theta along opposite direction, and to balance the scenario you have to give the same thing to here. So then this side will get cancelled, equals 0, because like L theta upwards plus L theta downwards, right? If you are going to consider the vector addition, L theta upwards plus L theta downwards, here the resultant will be now 0, right? You know that, right? How you get it? L theta minus L theta. But if I am going to consider here it is not 0, here it will be x1 minus L theta. See, that is why it is x1 minus L theta. See, now you got the point, right? So why it is minus, you know that when you're going to consider the application, right? Now here this is the mass, right? This is the spring, right? So now this mass is moving a displacement of x1 along the upward direction. That means this mass is actually pressing the spring along this direction, so the reaction on the mass is along other direction. But the considered motion is along upward, so that is why here we are getting minus, right? Now, like in the similar way you can apply to this one. I think I do not need to explain that, right? The same, by considering the same scenario you can apply to this one, right? Here, because in here also you know that there are two ends. If you're going to consider for this mass, this end is going along the downward direction by x2, where this end is moving a direction, moving along the downward direction by a distance of L theta, right? Because of the motion of the bar, right? So the same concept you are going to apply here. Then to here you are going to obtain an equation called, right? But here now see the direction here you are going to apply for m x2 double. Now what is x2 double dot? Acceleration, downward direction, right? Because now see the motion of this mass is along the downward direction. Now this is the way actually, yeah. Now see, now you can obtain the equation and see the same type, right? So now we have obtained this equation, right? Which is equation 1 for the beam, right? I theta double dot plus, you know that, right? So don't have to waste time on reading the equation, right? Now use this relationship, the relationship that is given by the simple harmonic motion, right? What is that? Theta double dot equals minus omega square theta, right? That means you know the acceleration toward the center, and here the theta is measured from the center, right? The relationship that is given by the simple harmonic motion, right? Okay. And now here, if you are going to consider the moment of inertia of the beam, right? So due to light weight, we can consider I equals 0, okay, right? So now this equation that you have obtained, okay? So now use this relationship, theta double dot equals minus omega square theta, right? So now try to replace, because now we are using this relationship to replace this theta double dot, right? But as the beam, right, the weight of the beam, we consider it as a lightweight beam, this I becomes 0. So now we are getting something like theta times this, and x1 times this, x2 times that, right? So now we have to arrange the final equation like that, right? Because our next target is to form some sort of a matrix, right? So that will be explained in the future steps, right? Okay. So now I hope this is okay with you, right? Carefully see the steps, right? Because I want to save time, right? So now consider equation number 2, right? So now equation number 2 we have already obtained, right? Like that. So what is this equation number 2? That equation number 2 is something that we have obtained for, you remember this mass, right? So now we have obtained this equation, right? So now to this equation also, we are going to use the relationship that is given by the simple harmonic motion, right? What is that? x1 double dot, that means the acceleration, right? That equals minus omega squared x1, right? Now see, this omega is the same for both the cases, right? What is omega? Angular velocity, right? So why we are using this relationship? To replace x1 double dot, right? So x1 double dot equals minus omega squared x1. So use this relationship to replace x1 double dot. So then you can form, you can rearrange the equation like that, right? So now in this equation also, form that equation according to this format, right? Theta times the remaining, x1 times the remaining, right? Something like factorization, right? Theta times that, like that, because we need this step, right? Right, okay, few seconds. Then equation number 2, equation number 2, you know that we have applied for here, right? To this mark, right? So then equation number 3 gives that mx2 double dot, you know that, right? So don't have to waste time to read that. So there we can use x2 double dot equals minus omega squared x2, you know that, right? So then use the relationship to replace x2 double dot, then you can form an equation like that, right? Then x2 times
whatever remaining, theta times whatever remain. So we'll stop at here. Matrix I will explain in the next part.
So now we have obtained equation number 1 and we have arranged it like that according to this format, theta times that, x1 times that. Okay, so like that for all three equations. We have arranged all three equations, right? Okay, so now we are going to obtain a matrix like that. Okay, so do you know how to obtain this matrix? Now in this matrix, right, this guy, right, let's call it displacement matrix, right? What is this? Displacement matrix, right? So what is this guy? We will call it stiffness matrix, right? What? Stiffness matrix, right? So now that is why I previously asked you to arrange it like that, theta times x1 times, and again also according to the same model, theta times x1 times. Okay, so now write x1 x2 theta in here. What? x1 x2 theta in here, according to this downward format, right? Okay, and then now carefully see. Now go to the first equation. In first equation it is x1 times minus scale. See, first equation it is x1 times minus scale. See, minus scale, keep it here. Then what is the next one? x2 times minus scale, right? So write that minus scale coefficient here. What is the last one? See, theta times 4kl squared. So write that here. So now according to the same order, x1 x2 theta order, right, just write the coefficients according to the second equation. See, this is the second equation. It is x1 times k minus m omega squared. See, k minus m omega squared. But here there is no x2. See, in this equation there is nothing called x2, right? So you can put 0. Then for theta we have minus scale. See, so like that you can obtain for this part also by considering the third equation, right? See, this is equation number 3. So now you have obtained this matrix, right? This matrix times this matrix, right? And the next thing, now consider only this guy, this matrix, right? Okay, now consider this matrix and take the determinant of that. Do you know how to take the determinant of a 3 by 3 matrix, right? I will teach you that. Okay, now we have to take the determinant of this matrix, right? This is the way, right? First consider this term minus scale, right? Then cut this line, minus kl times, just cover this line, then you have to do something like this into this minus this into that, right? Okay, let's see how they have done. Minus kl times, okay, minus kl means the first guy over here, so cover this line, this into this, nothing, minus this into this, now minus this into this, it will become a positive. See, okay, then the next thing, now consider this guy, second guy, right? It is minus scale, right? Okay, so the way to consider the second guy is put minus times second guy. What? Minus times second guy means minus into minus, this will become positive now. See, kl, right? That is how it comes. Take in the determinant, that is not a part of this lesson, right? It is about like matrix lesson, but doesn't matter, I will teach you that. So minus times the second one, so minus into minus will become positive here. So cover this line, again I will tell you, cover this line and just cover this line. Then what you will have if you cover these two? See, this into this minus this into that. Now here 0, so you don't have to worry. This into this will come. See, k m omega squared into minus scale will come. See, k m omega squared into minus scale will come, right? Then the order is positive coefficient, negative coefficient, then again positive coefficient. That means positive 4kl squared times, positive 4kl squared times, cover this line. What you will have? This into this only. See, k m omega squared whole thing squared, right? So now you know that. So now we have obtained the determinant, right? Okay, so let's go to the other page. Now what is the next thing? Now next thing is to simplify, right? Next thing is just to simplify, right? Then if you simplify, you will obtain something like that, minus kl times k m omega squared minus kl times k m omega squared plus, if you just simplify the previous one, the positive 4kl squared times k minus m omega squared. Just take these, See, this and this you can add, right? So it will give you minus 2 times this guy, that means minus 2 times KL squared m. See, this guy also same, this guy also same, right? So that is why minus 2 times this guy, right? Then this one. So now carefully see, now this is the most important part, right? Okay, so now here see, here k m omega squared is common, here k minus m omega squared is common. See, k minus m omega squared and k minus m omega squared, that's a common part, right? But even though if it is a common part, be very careful, never cancel that. Okay, I repeat, never cancel that, right? Okay, wait, but consider this kl squared that you have here. Here you have kl whole thing squared, right? And here you have kl squared, right? Here you have kl whole thing squared, here you have only kl squared. Wait, now but consider this kl squared term, because here you have kl squared term, but here you have k squared l squared term, right? Okay, doesn't matter, that means 1k will remain if you cancel, right? So now consider kl squared does not equal to 0, and you can cancel that. So if you cancel kl squared from here, k will remain, so that is why you have minus 2k times k minus m omega squared plus 4 times, right? Plus 4 times k minus m omega squared whole thing squared, right? So now you will have this guy, right? So from this guy you can go to this guy. How? You can just expand this, right? Then minus 2k whole thing squared, positive 2k m omega squared, right? And then this guy you can simplify, right? This like k minus m omega squared whole thing squared you can square, and that answer you can multiply by this one, right? So then you will be getting 4k squared minus 8k m omega squared plus 4m squared omega squared equals 0, right? So then you can simplify that up to here, right? Carefully do the simplifications and please check, right? So now here, right, after obtaining this one, divide the whole equation by 4m omega squared, which is not equal to 0, right? Divide the equation 4m omega squared is not equal to 0, right? So then you will be obtaining this one. If you divide from 4m squared, right, then you will obtain this one, right? Carefully check. So now if you simplify that, omega squared, okay, anything you can cancel. Yes, m to 1 m you can cancel, so you will be having k omega squared divided by m. This you can simplify in 3 divided by 2. Here after simplifying you will be getting k squared divided by 2m squared equals 0, right? So actually this is the answer, right? So this is the answer for the frequency